Hello, everybody. My name is, I'll leave my headphones on. Name's Tyler Gibson. I'm a software developer at Microsoft, and I work in an organization called Commercial Service Engineering. Our primary mandate is working with external partners to solve problems that haven't been solved before and help industries innovate and move forward. So what I'm here to talk about today is a project that I started with my team back in March this year that we call the 3D Streaming Toolkit. This is an open source project. It's available on GitHub. It's MIT licensed. But we're going to go through I'm going to go through why we built this and what you can use it for and the kind of path we took along the way, because we learned a lot. So to set some context, this is all about 3D stuff. So I do a lot of work with mixed reality, augmented and virtual reality. And one of the big problems that we have in this space is that we have computing power that is literally growing exponentially. So this is one of my favorite visualizations. This is just showing the number of transistors per chip on the largest commercially available single chip, starting from 1965 when Sir Gordon Moore put out his theory of Moore's Law, and following through to actually now last year. So as you can see, the number of transistors per chip has gone through the roof. Sometime in 2014 is when the world reached a point where there were as many transistors in the world as there are neurons in our brain. That was a few years ago. Now we're well past that. The problem, though, is that the vast majority of this computing power is still locked onto cables. So it's locked in data centers and it's locked on desktops. The amount of compute power, especially GPU compute power in the world, like 95% of it is in data centers that are being used today primarily to do machine learning, and on desktops primarily being used for gaming. And the issue with that is that, I'm sure as we're all aware with the Wi-Fi issues we've been having today, we've become, over the past 10 or 15 years, a mobile world. Everybody runs from their cell phone, especially the next generation, kids today, the 12 to 15 age range, they don't even really understand why you would have a cord connected to anything. Everything's wireless, everything's mobile. But when you look on the capability side of mobile platforms, including high-end smartphones, while the specs and numbers tell you that, speeds and feeds tell you that things have gotten progressively faster, the reality is that the limits of thermal throttling and battery density have really limited us for the last 5 or 6 years. So I know the numbers just came out for the iPhone 8 and iPhone X a few days ago, and it's saying, it's just as fast as your desktop or faster, and it's this new era of computing. But the reality is it can only maintain those numbers at boost for a few minutes before thermal throttling happens and it has to clock back down. And you only get a couple of hours before the battery runs out at those speeds. So how do we overcome these kind of diametrically opposed things? Well, we started working last year with a company called Aviva in the UK. They're an engineering services company that focuses really on oil and gas. And the easy way to think about what they do is they provide applications and services to build and design things like oil tankers and refineries. And one of the big challenges that they have today is that they want to move into this new world of mobile. They want to embrace HoloLens and mobile AR, VR headsets, Gear VR, Oculus Rift, Vive. They also want to embrace where people are today, being able to deliver mobile applications to their customer base. But they have this real world problem that their average model is on the order of 500 million to 1 billion polygons. And they can't simplify things. They can't just reduce meshes or do a lot of the tricks that you see in gaming because the accuracy matters. These are real world, extremely precise engineering platforms that have to be accurate. And so they came to us with this problem, and we said, well, I don't know, let's see if there's a solution. So last fall, about this time actually, we put together a proof of concept. We went through what we call a hack fest. So we spent a week together to see if we could actually render things in the cloud and send them real time via video down to the HoloLens and send input back so that it looks like a fully interactive experience. And it worked. So said, all right, this is interesting. But then it took us another 5 months of research and investigation to say, okay, how do we go from this proof of concept to something that a business can actually take to market? And where we landed with that is a couple of things. So the big problem we had in the proof of concept was video transport. How do you take a video signal and send it over the internet in a way that's robust, in a way that is reliable, that can take into account all the crazy stuff that can happen in between. And after a lot of research and explorations, we landed on a technology called WebRTC. Has anybody here even heard of WebRTC? Show of hands. Oh, sweet, a few people. Awesome. So for those that don't know, if you've ever used Facebook Messenger, Google Hangouts, Skype, Apple FaceTime, Line, WhatsApp, and you've ever done a video chat, they all use WebRTC. It is the standard way to send video for real-time communications. It's been around for 11 or 12 years now. It was started by Google. It's an open source project. It's supported by every major browser. And as of now 3 weeks ago, Apple has native support for it in both iOS and macOS and Safari. So there's a lot going for it. It's very stable because it's been around for a long time. It has great platform support, and it's super stable. The other half of the puzzle, and this has been the challenge for a long time, was the technology from Nvidia called NVEncode. So how many people here remember OnLive, the game streaming service, a while ago, and how it was promising this awesome game streaming stuff? Well, turns out they couldn't make any money, and the reason they couldn't make any money is they were both running the games and doing the video encoding on general CPUs. They weren't using GPUs under the cover at all, which is incredibly expensive. NVEncode is this technology from NVIDIA that we kind of almost discovered by accident, that it turns out has been in every NVIDIA video card since 4 or 5 years ago. Laptops, desktops, mobile platforms, and data center. And that data center piece was the really important part. So on every NVIDIA GPU, there is dedicated hardware to do real-time video encoding and decoding. So to give you an example, if you want to do game streaming, like Twitch, right? If you do game streaming and you encode on your CPU, quad-core i7, you're going to use about half of your CPU across all cores to do real-time encoding for H.264 with 1080p. You can forget about 4K, that isn't going to happen. And it takes somewhere between 15 and 30 milliseconds to encode each frame. NVEncode can do 8K at 60 frames a second with less than 1 millisecond of encode time, and it has zero impact on GPU or CPU. It's completely dedicated in hardware. So if you guys do anything with video and you have NVIDIA cards, go check this stuff out. It's really cool. But the trick for us is that all of the GPU instances that are in Azure, they're in AWS, anywhere in the cloud that runs like machine learning GPU instances has this capability, and it's turned on. We just found that not a lot of people were using it yet. So those two pieces really enabled us to go down the path of building this toolkit out. So where we started was with the way WebRTC works today. So WebRTC is inherently a peer-to-peer structure. So it assumes that every client is a server and every server is a client, because you're both receiving audio, video, and messaging, and you can send it. So this is the basic architecture of how WebRTC looks today. the stuff that I'll call out in the middle, the signaling server, stun, and turn. Those are the three things that took us a long time to understand what they did and how they worked. So signaling you can think of as like a real-time phone book. So when a client comes online, it sends a message out and says, hey, I'm online, I can accept calls, and here's my information if people want to call me. And so it sends that up to the signaling server. And the signaling server essentially keeps a list of clients that have connected to it and are active so that other people can connect. So when client 2 connects to the signaling server, says, hey, I'm available, signaling server sends back a list and says, here's all the other clients that are available that you can talk to. The stun server is basically a service implementation of whatismyip.org. In order for the signaling server to know what your information is, it needs to know what your IP address is, what your network configuration is. And in traditional terms, this is what stun does. Google maintains hundreds of public stun servers around the world to use, so basically no one runs their own stun instances. But it effectively goes up and gives you your external IP address, gives you some network configuration information about your network adapter, so that signaling can tell other people how to connect to you. And all was fine and dandy in the world until 2014. Because it turns out there was a problem with stun and signaling. And that problem was it worked too well. So if you were behind a VPN or a proxy, and you called out to WebRTC and said, hey, signaling server, here's my information, stun, tell everybody what my information is, it would just bypass everything. So your VPN, we don't need VPN. We'll tell the whole world what your actual internal network addresses are and everything in between, therefore bypassing all that security. It was a really, really big security issue. So 2015, everybody fixed it. The problem when that was fixed is that now all of a sudden, if you're behind any closed network configuration, you basically couldn't use WebRTC. That's where turn comes in. So turn is a relay server that just acts as an intermediary point so that nothing has to come in. It allows clients on both sides to communicate out and use the turn server as a relay in between. It acts effectively as its own VPN between 2 points. The advantage of that is it gets us back to the point where, as users of this technology, you guys don't have to worry about NAT configuration and proxies and firewalls and port forwarding. All that stuff goes away. The traditional downside of a turn server is it's very expensive because you're sending all the bandwidth for audio and video through this relay. But that's the solution that they came up with. So we said, all right, how do we work within WebRTC in a way that is friendly to the community? And we looked at their stack. We looked at the way things were built. We said, okay, first step is extending the video encoder. So we took the existing encoding pipeline and plug-in architecture of WebRTC, and we simply added NVEncode to that. And actually, our plan is to contribute this work back into the WebRTC source so that hopefully sometime early next year, Chromium, Firefox, and others will just have this built in. So, which is very helpful for things like desktop and screen sharing. It takes I don't know if you guys have ever tried to share your desktop over like Google Hangouts or anything like that. And you watch your CPU spike to like 100% and everything bogs down. Well, if you use NVEncode, you get that nice 0% impact. So that was step one. And then step two was, okay, how do we add 3D stuff to this? So today in WebRTC, you effectively have the ability to hook in through whatever client you're in, use the video encoder, and capture from a webcam. So what we did is added a bunch of shims and plugins for 3D applications. Right now, we support DirectX. I am very hopeful that in the next couple of months, we'll be able to open the doors to OpenGL. There's no technological blocker to it. It's just a matter of finding someone who needs OpenGL in their project. for us to go and light that up. But we added these 3D application shims for Unity and DirectX on Windows. And then the second piece you can see there is the 3D metadata. So the way WebRTC works from a communication standpoint is everything is what they call a data channel. It's basically an open UDP connection that you can send arbitrary data over. And it just happens that WebRTC built a couple of special data channels to make things easier, one for video, one for audio, to handle things like jitter management and latency changes and network congestion so that you don't have to deal with all of this. So we added a simple metadata channel for 3D metadata. So today, all we're really sending over that is camera transforms, so what you're looking at in a 3D scene. But it's just a JSON payload at the moment. You can also send binary data, which we have sample code for. So you can extend this to do things like with the HoloLens, for instance, taking the SLAM data, the constructed mesh of a room that you're in, and sending that back over the wire to the server to do more processing on. Or if you want to send locally captured data about object recognition or voice detection, things like that, it's a really easy way to send that data back in an asynchronous and extremely low latency manner. The other piece to this is that in a streaming situation, even though WebRTC is a peer-to-peer kind of framework and technology, we're really operating in a client and server structure. So we needed to do a little bit of differentiating work to be able to tell what's the server and what's the client. And you can see the dotted lines drawn because physically it's still peer-to-peer. Anything can be a client, anything can be a server, but chances are you're not going to find an Nvidia card on many smartphones today. In fact, none that I'm aware of right now. So sending video back is very expensive from those kinds of devices. On the flip side, on those devices, we do need to send back that input channel, camera transform and location. So we did a little bit of work to differentiate what's client and what's server between those two. We also ended up writing a signaling server. So this is just a Node.js web app. It's very tiny. I think it's like 40 kilobytes for the source code for it. You can deploy it on any standard Node.js service or server. But we wrote our own for a couple of reasons. So the first reason is if anyone has messed with WebRTC, there's a ton of getting started tutorials, like level 100, that basically tell you to go copy and paste some stuff, and everything will work in your browser, which is great, and it's true, it works. It turns out if you want to run WebRTC in native applications, like iOS and Android and desktop, there's very few people in the world that have done this, or at least that talk about it publicly. And most of the big signaling servers that are out there are wrapped in these things called MCUs, multimedia control units, that are primarily designed to integrate with VoIP and SIP solutions from telcos to do like big enterprise like voice over IP services, which we're concerned with video, not so much with telephony. The last piece, which is honestly still very surprising to me, is, to my knowledge, we're the first people that have written a signaling server that actually supports HTTPS. All the samples out there, all of the MCUs that we explored, everything's just done over HTTP, which is really bizarre that you'd send like full network stack information about clients over open HTTP connections. So we solved that. This thing uses HTTPS. You can also turn that off if you want to, but you shouldn't. And we also did some work to clean out inactive connections. So there's lots of instances where one client, like a client can crash, or you exit, or a network connection drops, and you're not able to tell the signaling server that you're no longer available. So we added basically some heartbeat functionality to periodically check in and make sure that a connection is still active so that things know when to close down gracefully and how to restart themselves. And then, of course, logging and monitoring so you can actually see what's happening with this stuff. For the turn server, this was both really easy and very interesting. So there's an implementation of Turn called CoTurn from Google that is basically like the industry standard. It conforms to every standards body spec, every RFC. It does everything the way it's supposed to. It's open source. It's available. The problem that we found is that before this project, the only out-of-box implementations to deploy this to a cloud provider were for AWS. And all of the Docker-based deployment scripts have been broken for like 2 years for AWS. So you couldn't actually deploy this in any systematic way. You'd have to go grab the Docker container manually, build up your orchestration around it, and deploy it. So we wrote some simple deployment stuff for Azure. So if you want to run your Turn instance as Azure, it's sort of one-click deploy. There's a little bit more to it because we do strongly recommend using Postgre or real database as your storage rather than SQLite. You don't have to. But with the Postgre implementation, the only thing that keeps it from being kind of one click is you need to set up Postgre and then run our script. So in addition to that, we extended it. The default CoTurn uses static credentials. So you assign username and password to a user. They authenticate with a relay server, and that's how you get that interaction. Of course, the problem there is if anyone sniffs or compromises that username and password, they now have an open internet relay to secure any 2 points between each other with secure traffic, and you're paying for their bandwidth. So a little bit of an issue. So we implemented a authentication scheme, which I'll go into a little bit in just a second, to instead use OAuth and temporary credentials. Right now, the default configuration is we cycle those every 24 hours. You could cycle those temporary passwords as often as you like. But again, just trying to make this solution something that you guys can actually build on and take to market if it's something that you want to scale up into commercial and into production. And then, of course, cert management, all the basics of securely managing a service. And then the load balancing coming soon is actually no longer coming soon. We've published that. So again, to my knowledge, while CoTurn has had this load balancing capability, there's not been an open source project to actually expose this in an orchestrated manner. Essentially, these relay servers, you can set one relay as a load balancer, and it will parse out traffic to a managed set of other relay servers so that you can scale this out beyond just a single one. So we provide step-by-step and ARM templates for Azure to deploy those out. So that auth stuff I was talking about. In a nutshell, you have the ability with our toolkit to do everything secured. And you don't have to use this just for 3D. If you guys want to build WebRTC into your existing application and just do standard video chat or messaging, you can use these services independent of the rest of the toolkit, and they will work with any WebRTC implementation that's out there. So on the Turn server, we support TLS and DTLS for security there. As I mentioned, HTTPS for signaling, as well as our identity management service samples, temporary passwords for that relay service. And then we have OAuth 2.0 for everything else. So both client and server and relay and signaling, everything works with OAuth, token management, and shared secrets. So our implementation is using Azure Active Directory's B2C services to implement this, but you can use any OAuth provider you want. It's not even really a matter of tearing it out, just pointing it to anything else if you want to use it. I think in the samples right now, we light up Google and Facebook for consumer logins for that, but you can turn on Enterprise Active Directory, you can turn on Microsoft accounts, whatever set of providers you want to use, you can use. So the way this works in practice, you've got your client, so whether it's HoloLens, mobile, web, desktop, and you got your server. And you got your signaling server up there. And so the client says, hey, I'm available, and I can work on stuff. And because we use Relay for everything, so that you guys don't have to worry about network negotiation. The client then connects and says, hey, relay server, I need to connect to you, and it needs temporary passwords to do that, which it doesn't have yet. This is where identity management comes in. So the client says, all right, I need to let the service know who I am. So it logs into the identity management service. It's where you get your nice OAuth tokens. All that's shared. Identity management sends back and says, okay, here's your temporary relay password. So now it can authenticate with the relay server. And we use Active Directory B2C right now to broker all that with whatever login service you want so that you can get access tokens to talk to all the above. The same thing happens on the rendering server. The only difference is on the rendering server, that's a trusted executable. So we include the secrets in the executable in runtime so that you don't have to actually have an interactive login on the service side. But other than that, it acts exactly the same way. It gets access tokens, which have their own timeouts, so that if you have a service node that's compromised, for instance, you could cycle your secrets, and any running instances will time out and no longer be valid after your timeout period. So, and everything along the way is running in HTTPS and TLS, DTLS. So if you're interested, you can go to the link above, Catalyst code/3D Toolkit, clone it. Right now, you do need a Windows machine. It uses Visual Studio 2015, Update 3. The README will show you the couple of prerequisites, but essentially, open this, open the solution, hit build, and you can run this in a local instance demo fashion in about 20 minutes to see how it works. So we provide a bunch of stuff in the V1 release that's out there. As I mentioned, we've got the basic NV encode with WebRTC, which we're now working on contributing back to Chrome. We've got the basic 3D data channel extensions. We've got all the services that I mentioned. Those are all in open repos, and they're all published to Docker Hub, so you can use the Docker container images if you want to directly. And then we've got a ton of sample apps. So Unity-based, we have a HoloLens client and a Win32 desktop client, and we have a Unity server as well. A note, if you go read the README, you'll see this at the bottom. It is currently against Unity's terms of service to run Unity as a server that primarily streams video. So if you want to use Unity, you can. You just need to go talk to Unity individually and get licensing to use it that way. We are working with them to kind of remove or alleviate that restriction, but it is there today. For DirectX 11, we also have a HoloLens client and a desktop client, and we have a couple of DirectX desktop server samples. We use Node.js for the signaling server, and we use Azure B2C for all of the identity management stuff. So where are things going? So there's a reason we call this a toolkit and not like the 3D streaming framework. The big reason for that is being able to send complex 3D stuff to mobile devices is really the first thing that's blocking a lot of our partners. As you can see, the first bullet point on there is the next big thing that I think a lot of people in the industry, not just in this use case, are really looking for, and that's context and state management. So think of this as basically multiplayer gaming for not gaming. It turns out that even in productivity, enterprise, commercial scenarios for AR, VR, MR, that interacting with multiple people is kind of important. And there's not a lot out there today outside of the gaming world to light this up. So that's something that we're looking at exploring next year, actually, is perhaps creating or extending this toolkit to handle that stuff. The next bit is outside-in capture. So the way our toolkit works today is you basically integrate our plugin into the source of your application. So it gives you a lot of control over what you output. So you can have mixed mode apps. We have one partner, for instance, that has a desktop app, and they just want to essentially mirror a small portion of that desktop app out to HoloLens to have like a peripheral experience. So you have one person on the desktop app, you have another person in the HoloLens, and they're working together in a shared environment. And our plugin works really well for that. It also works great if all you want to do is just mirror an entire app out to HoloLens or iOS or Android. But there's a lot of cases where you want to do outside in, where you have an existing application that you either don't have the source code for or don't have licensing rights for, and you just want to mirror that thing to a remote device. And there is a solution for that in the NVIDIA Capture SDK. There's some licensing stuff we're trying to work through on the open source side so that we can integrate and use it, but that's another thing that we want to light up. And then, of course, OpenGL and Linux support. I personally really want this because I want to get all of our stuff to work on Docker. I want to be able to containerize the applications on the server side to make them much more easily deployable. And our framework supports OpenGL. We just haven't built it yet. Our clients to date, our partners to date, have been more focused on DirectX and Unity. So if you guys have really cool OpenGL stuff you're doing and you want to use our toolkit for it, like get in touch with me and we'll figure out how to make it happen. And then along with that, using Kubernetes, so actually having real orchestration to deploy this out to scalable commercial use cases. And then on the sample app side, as I said today, we basically have HoloLens sample apps and desktop sample apps. We want to not have that limitation. So there's actually a PR right now that I'm hoping we'll get in the next couple of days for iOS. So we have an iOS client. We actually do have a web client as well. And we've got most of these in the works kind of internally within Microsoft. There's a bunch of individuals who are just really interested in the project, and so they're building it on their own time. So I'm hoping over the next month or so, the Xamarin client is in process, that we'll be able to publish that. Same with React Native, same with Android Native. So we should be able to fill in these gaps pretty quickly and have a nice multi-platform solution. And again, the nice thing with all this stuff is that you can use this for 3D streaming, but if you just want to make a iOS native WebRTC app, like you can just go grab our iOS native app sample and not use the 3D metadata data channel, and you've got an iOS web client or an iOS WebRTC client. So it's more flexible than just our single use case. So that's kind of where things are today. I want to do one more thing, and then I want to show you guys a demo. Given the network conditions here, I'm going to do a local demo. Unfortunately, I can't. Normally, I attempt to do a cloud-based demo, and then about 50% of the time it fails spectacularly, and there's that awkward silence, and while I'm trying to figure out where the latency is coming from and what's going on, but I think all of us have seen the Wi-Fi here, and unfortunately, this building is like a bunker, so my nice LTE hotspot has no connectivity whatsoever up here on stage at least. If I go out that door, it's fine, but not inside. But before I do that, I want to mention the folks who really built this. I was just the guy who got it started, but these folks, this is the core team that worked on this, and it's incredible how much we've learned. We all went into this not knowing anything about video transport or real-time communications or native Unity plugins. So we've learned a ton over the last 6 months building this. So Ben Greenier, he's based in Boston. He's like the whiz kid of the team. First time I met him, I was like, are you actually 18? What's going on here? But he is a Unity and gaming expert that came into our organization recently. So he's been responsible for a ton of the HTTPS support and SSL support, building that in. Chase from our partner Aviva, he basically wrote everything with the Unity server and did a ton of work abstracting our stuff so that it can run as system services, so you don't have to be interactive with the server side of things. Fong Cao is probably the best Android developer I've ever met ever. He wrote basically all of the native code, which is a lot. Almost this entire toolkit is cross-platform C++. I am not a C++ guy, but, well, I guess now I kind of am because I've lived in it for better or worse for 6 months. But Phong wrote a ton of that stuff. He wrote all the DirectX clients. He wrote both of the DirectX servers as well. Anastasia, she's responsible for all the services stuff. So if you'll notice in the links, it's all under her GitHub account for all the turn, co-turn, signaling server. She wrote all of that and stood it up and figured out how to get it all to work. Just a tremendous amount of work. And then Andre is our video guy. So before Microsoft, he worked at Intel on their QuickSync video encoding. So he wrote basically the entire video pipeline on both sides of things. So I always like to make sure that people get their due because I'm just the guy that comes and talks about it. I was more the designer PM for this project. Like, these are the guys who did literally all the work. I just merged stuff on GitHub. So you can follow me on Twitter. Get in touch with me if you want to use the toolkit and you have problems. We've transitioned everything over to the GitHub project. So if you have issues, log issues there. If you want to submit PRs. We're very active on the repo. I also encourage you guys to go check out our team's blog, microsoft.com/reallifecode. So my team is now about 130 people that we all do projects like this. So we write things that we call code stories that talk about how we built the projects we built and why, what the scenarios were for them, and then link to open source repositories like ours to show the implementations for those. So if you're doing anything in machine learning or bots or IoT or mixed reality or virtual reality or 3D, like, go up there because we have a few hundred projects that we've done across the spectrum of technologies, and every one of them is open source. So all the code's there. You can build it yourself, you can run it yourself, and you can go through the scenarios of why we did that stuff. So with that, let's pop over to, hopefully, to demo time. I'm going to give it a shot, and we'll see how it goes. So I'm just going to start up here. So I'm going to make sure that our stuff is configured properly. Okay, good. So actually, we do everything in, oh man, you're not able to see that at all, are you? There we go. Let's make that nice and big. How many, just out of curiosity, how many people here have ever tried Visual Studio Code? How many people like it? How many people really hate it and gave it up and went back to Sublime? Oh yeah, no hands. I like that. If you haven't tried it, Visual Studio Code is a cross-platform code editor. It's available on Mac OS, Linux, Windows. Super lightweight. It's pretty awesome. There's plugins for everything, and it's open source. So I encourage you guys to check that out. So all our configs are JSON-based, so it's easy to edit stuff, rerun the executable if you want to change things. So in here you can see turn server configuration, which I currently have disabled because internet access sucks, and then a signaling server that we can connect to so we can get basic stuff running. So right now I've disabled all the OAuth flow just for demo purposes. We'll see if we can actually reach the internet. Yes, we can. Okay. So this is our server, and then we'll pop up. You can see all the clients that get built. And I'm just going to make sure the client is also configured the same way. It is. All right. And so we'll spin up the client. And so now you can see as soon as I connect with the client and server both see each other because of the signaling in between. So when I click to connect, now what's happening? So the server here is running our demo scene, and the client is viewing that scene with H.264 video. And so as I move across, you can see the client and server are moving. You'll notice that there's lag on the client, but the server looks perfect. That's because my laptop is not plugged into power right now. So it's not any trickery. There's no actual latency there. It's the goodness of Windows power management. But we basically have all of the interaction is coming from the client, being sent back via WebRTC to the server, and everything kind of works like magic. We notice that, or from what we've seen from a latency perspective, got myself in a weird place in the scene. So what we've seen from a latency perspective from the cloud under normal use cases, we did all of our initial testing from our data center in San Antonio, Texas to Redmond, Washington, which is about 2,200 miles. Round trip times are about 60 milliseconds, which is really good. For touch and mouse driven interfaces, if you're under 100 milliseconds, it's basically imperceptible amount of lag. When you're closer, it's better. So I know that in Europe, we have both Ireland and Northern Europe, I think, are the two main data centers here, which are significantly closer. But basically, the limitations of our framework are down to the point of time of flight at this point. So it's physics. It's how long it takes the electrons to travel from end to end. Our overhead for decoding and encoding and message passing is somewhere on the order of 8 to 10 milliseconds. So it's really, really fast stuff. So that's kind of what I had to show for you guys today. If you've got questions, if you want to see other stuff, I've got a few minutes left. Thank you.
Does the toolkit support sending stereo video for
yes,
VR?
It does. So it's a really good question. So not only does it support stereo rendering, it's actually configurable in real time. So you can have a server instance that when a client connects, the client says, I'm either a mono client or a stereo. If it's stereo, the server actually doesn't have to restart. It just turns on stereo rendering, sets the video output to that, and sends it. When that client disconnects and a mono client connects, it can go back to mono rendering. So all that happens at runtime.
Do you have any way to compensate the latency for that?
There's no additional latency other than if there's network congestion or something.
But for VR, it's probably a bit high.
Well, to give you a comparison, so the instances, at least in the cloud, so you can run this toolkit on a desktop, on a laptop. I mean, you can see me demoing it here. There's no restrictions on running it in the cloud, but if you do, you're running that on Quadro hardware, so you get a lot more video memory. I think the smallest GPU instance you can get on either Azure or AWS has 12 gigs of video memory and has essentially the rough equivalent of two 1080 GTX TIs that are running. So you can push an unbelievable amount of polys and data through those things. And that's the smallest. You go up to what they call the NV24 instance, and you actually get 4 GPUs that are all bound together. So you can push upwards of 1 billion polys that are textured, lit, and shaded at 60 FPS without any problem.
Can you do any additional processing at the endpoint? With the metadata you sent, for instance?
So it's completely open. You can do whatever you want with it. That's why on the client side, we are working on not only the native clients where you're just taking a video signal and spitting it out, but for instance on HoloLens, we're spitting that video signal out into a Unity application. So you're not limited to just showing the video from the server. You can overlay other holograms, you can overlay other 3D, you can composite that remote render into a full-fledged 3D application to fit whatever your needs are. So that's really why we designed the toolkit the way we did, was so they could be as flexible as possible for different use cases.
Can you stream multiple channels?
What's that?
Multiple channels, like layers, for instance, like a depth layer. So you could do some additional compositing on the client.
It's really interesting. So it's something we have not done yet, but we've...
You're thinking about it.
I can say that there are a couple of partners that really want that, to essentially be able to treat the video signal that's coming in as a point cloud. so that we can have Z-depth buffer on the video and layer each pixel in Z. It's definitely possible, but it's not something that we provide out of the box.
Vulkan support?
So currently this is Nvidia only. Yeah.
Well, Nvidia supports Vulkan. So.
Yeah. I don't know why it wouldn't work, because under the covers, we're basically just using CUDA. It's independent of the actual rendering technology. But build it and send us a pull request.
You've mentioned you are implementing the OpenGL support, so
Yep. Yeah, it should work.
Vulkan should get a lot more traction in the future.
Yep.
Well,
Cool.
that's it.
Yeah, thanks.
I've got no more questions. Thank you.
Anybody else? No. Yeah.
Hi. Thank you for your presentation. I'd like to ask is there an alternative to NVENC code, for example, for Intel or AMD? Are you thinking of implementing something like that?
So AMD does have a equivalent for video encoding. The issue is that AMD has no penetration into data centers. So one of the things that makes this affordable and approachable from a commercial scale-out perspective is that with a few exceptions, whether you're going with Azure, AWS, Google, Rackspace, wherever you're putting your cloud infrastructure, if you use GPU instances, they're all going to be from NVIDIA, and they're all going to be the same standardized set of hardware. So everything's very portable across cloud providers and vendors. At least to date, AMD doesn't have that focus on the cloud GPU side. So that's why we haven't focused on implementing with them. But if you want to extend WebRTC to support AMD stuff, it's actually going and looking at the code that we've written to write the plugin for the NVIDIA side should actually make it pretty fast and easy to extend that to AMD or like Intel for QuickSync, for instance. So it's not something that, again, is necessarily blocked, but for the use case that we've at least started with, it just didn't make sense to go down that route right now. Yep.
Thank you.
Yep. Anybody else? No? Well, cool. Thank you, guys. Appreciate it. I'll say, regardless of what you want to build, if you want to stand this up and you don't have Azure subscriptions, come over to the Microsoft booth. We have Azure Cloud Passes. I think you get like $200 a month in free consumption, something like that. And for your projects here, if you're working on the hackathon and you don't have a cloud solution yet, you don't have a place to deploy your stuff, come over and grab some passes there. And if you need help on anything relating to the challenge especially, come over to the Microsoft booth and ping us. And for me, in particular, if you are working or interested in anything relating to AR, VR, MR, come find me. IoT, come find me. Happy to help you guys out and talk to you about it. So, thanks.